Today I want to finish up this discussion of relativity by looking at general relativity. So far we've been looking at the special theory of relativity. It's special because it applies only to inertial reference frames. In other words, you have to be moving at a constant velocity relative to the outside universe or whatever. If an object is not moving at a constant velocity, it's accelerated, then special relativity won't work. The laws of physics in normal won't work from that reference frame. For example, if you're in a bus and you have a ball just sitting in the aisle, object at rest stays at rest unless a force is acting on it. If the bus driver slams on the brakes, the ball is going to begin to roll forward, as though there was some fictional, mysterious force just pushing it forward. In reality, there's no force there. It's simply you're in a non-inertial frame, and so the laws of physics don't work in the same way. From a person in an inertial frame outside of the bus watching, they see correctly the ball continuing forward in a straight line at a constant speed while the bus slows down underneath it. So, dealing with non-inertial frames, you could rebuild the laws of physics from that non-inertial frame inside the bus. And in that rebuilt laws of physics, you'll find there is a mysterious force that emerges that pushes the ball forward. Okay? But we'd prefer not to do that. So, general relativity basically tries to take the rules of relativity that we already know and apply them to non-inertial frames as well. And turns out that was rather difficult to do. Einstein put together special relativity in a year or so. General relativity, he started working on it immediately. 10 years later, he finally came out with it. Now, the key issue here is trying to deal with acceleration in terms of those Lorentz factors and all that, which just didn't work real well because there's derivatives involved and it gets annoying. The flash of insight he got in trying to deal with acceleration was realizing that acceleration can be caused by gravity. So here's a thought experiment that he did that kind of set it straight in his mind. Imagine you're minding your own business and me and the rest of the physics class sneaks up and knocks you out with some of my chloroform. And then you wake up and you're in a room and you're floating weightless. So what's going on? There's no windows, you can't see outside. It's possible. Now, let me draw it. Here, oops. I need my pen. There's the room, and here you are floating in the room. Well, you're not floating real well, are you? But whatever. Why are you weightless in that room? Well, there's two possibilities. Number one, you could be in outer space with no gravity, and you're floating because you're in the space station or whatever. So, we spare no expense in our pranks here, right? But the other possibility is you might be in an elevator that we cut the cable of, and you're freely falling to your doom. You would feel weightless as the elevator fell because the floor is falling out from underneath you as fast as your feet are falling. And so there's nothing pressing you to the floor anymore. The key issue here is you don't know which one it is until you look out the window. Alternatively, and I'm going to draw another box here with a person in it. Let's say you wake up in a more normal situation where you're not floating. You wake up in a sealed room and there's normal seeming gravity there. Once again, though, that means there's two choices. You could be in a room on Earth with a normal gravity field pulling you downward. Or what if instead we actually, again, spend all the expense to send you into a spaceship firing its rockets, and the rockets are providing a thrust of exactly 1g. So you're in outer space, so there's no gravity. But the floor is being pushed up at you at exactly 9.81 meters per second squared. So from your reference frame, you see yourself being pressed to the floor. Us outside, we see you floating, well, not floating, but we see you would have been floating, but the floor is being pressed up against you. Back if you're on Earth, well, then gravity's pulling you to the floor. Which is the correct situation? Once again, Einstein realizes you can't tell without looking out the window. Okay? And that led him to what he called the principle of equivalence. Okay? And that states that acceleration that we have over here is identical to gravity force. Okay, they're not two separate things anymore. We've always been treating them as separate things. There's a force of gravity, or you're accelerating. Now, you've noticed this in your car. You hit the gas pedal, you accelerate, you're pushed backwards in the car. Einstein's saying that that is no different whatsoever from the way gravity works. Okay? So, another way to say it is there is no experiment that you could do to prove whether you were in a spaceship or you were on Earth affected by gravity. If you try to drop a ball, you let it go. On Earth, it falls at 9.81 because there's a gravitational field pulling it down. In space, you let the ball go, it floats there, but the floor rises up at 9.81 along with you and everything else, and so as far as you can tell, the ball falls to the floor anyway. Okay? So no experiment will distinguish the difference between a gravitational field or uniform acceleration. Which, by the way, that means if you could build a spaceship that could constantly fire its engines forever, you could constantly accelerate in space and always have artificial gravity. And really, in that case, there's nothing artificial about it. It behaves exactly like any other gravity. And that's Einstein's principle of equivalence. Now, that led him to understand general relativity, because now he could consider accelerations as though they were the same thing as gravitational fields, and then start using gravitational field equations, which were well known and understood, and applying relativity to those to explain acceleration. So, there's a lot that came out of this, obviously, that we can't discuss because the math is pretty horrible. But here's the thing. If you were to throw the ball, it would drop at a parabolic path because gravity is pulling it down. If you're to throw the ball in the spaceship, same thing. It looks like it's falling in a parabolic arc because the floor and you are coming up to meet it. Now, what if it was light waves? Okay? In the accelerating spacecraft, well, the light is traveling across the room at the speed of light, but you and the floor are moving up, and so it's going to look like the light beam is curving down. Now, clearly, if you're going any realistic speed, the amount of curving there is going to be so small you're not going to detect it. But again, thought experiment. What if you're in a spaceship accelerating at ridiculously high rates of speed? The curvature of the light wave, of the light beam, is going to be noticeable. Okay? So acceleration, you see light curving because you're accelerating up underneath the light. But what about a gravitational field? If the principle of equivalence is exactly true, that means the same thing would happen with a light beam in a gravitational field. The light beam should bend downward just like a falling object does. So, a consequence of general relativity, of the principle of equivalence, is that gravitational fields should bend light. Now, Newtonian physics disagrees. Objects fall because Fg equals g mm over r squared. You need that second m. You need the mass of the object. Photons, light, is massless, and so there should be a gravitational force of 0 acting on light. So gravity should not bend light at all. But if this principle of equivalence is true, gravity has to bend light. And so we have a way of testing general relativity now. We can look to see if gravity bends light. Now, we don't have any high mass gravity things laying around. And of course, notice, similar to before, just like you would have needed a high acceleration, you're going to need a massive amount of gravity in order to really see light bending. So, the most massive thing we have near us is the sun. So, they figured that the sun itself should bend the light of distant stars as it goes past it. Now, of course, you can't see the stars near the sun because it's too bright, except during an eclipse. So, if we come down here, there's the sun. See it shining. Here's Earth. Now, there's some distant star over here. Okay? When the sun's not there, we see the star at that position in the sky. But what if the sun is right nearby? Well, then the light from that star will get bent. And the star will appear to have been at a different place in the sky. Okay? The star is back here, its light bends, and it looks like it moves over to there. Okay? So, the gravity of the sun will bend the light around it. Again, the sun's too bright, you normally can't see that, but during an eclipse, then you can. So they can look, they know when eclipses are coming, they can look at exactly the locations of all the stars that are going to be in the area, and then during the eclipse, take a picture of that and see if the stars have shifted their position. If they have shifted their position, then gravity of the sun did indeed bend their light. They actually, Einstein proposed this in 1915, and there was an eclipse going on around then, but World War I was going on around then as well, so they just couldn't go and do it. After World War I was over, the first eclipse they found, they got together and it was one of the big, yay, post-war, we're getting along now, and went out on an expedition to South America somewhere, I believe it was, and checked the eclipse and found out that the shifting of the stars around the sun exactly agreed with Einstein's predictions. And so we have evidence that gravity does indeed bend light. Again, it's got to be light passing pretty close to the sun in order for us to notice it. And even then, it's not hugely noticeable. But if you take a more massive object, like a black hole, you get a lot of bending of light there. And you can actually get really interesting distortions of images from there. If you saw the movie Interstellar, where they orbiting a black hole, they were really realistic about how they showed that. You also can get around a very massive object like a black hole or a distant galaxy or whatever, something called an Einstein ring, where if the object is right behind the massive object, light coming both ways gets bent around. And so you see images of the object on both sides of the black hole. Or, if you get it just right, as a whole ring around it. So what you would actually see is there's the object in space and then a ring around it. That ring around it is the light of some other distant object that's right behind it that got distorted, or what we say gravitationally lensed, by the black hole. So that massive object, whether it's a black hole or a massive star or another galaxy, really, that massive object can act as a lens, and the gravity can bend or focus the light. And by analyzing that focused light, they can construct detailed images of something that's so far away that we couldn't have seen it well otherwise. So this gravitational lensing is a very, very useful technique. More recently, they've actually used it to find what they call rogue planets. There are planets, massive planets like Jupiter, and even maybe presumably Earth-sized planets out there just floating in deep space. They got expelled somehow from their solar system. Every so often, one will pass in front of a star. Obviously, we can't see these planets. They're not bright. Then they're far away. But if one just happens to pass in front of a star, we'll see a distortion, a gravitational lensing of that star. And based on the distortion, we can tell how much the gravity has bent the light. We can calculate the gravitational force, the mass of the planet, and other information about it. So they've discovered some exoplanets by this gravitational lensing technique. It's one of the major consequences of general relativity. There's a lot of other really, really major consequences as well that we can't really get into too much here. But for example, the way this bending of light occurs turns out to be a warping of space-time. So space and time themselves get warped and bent around a massive object. So a consequence of that is if you go near a massive object like the sun, time slows down. Very, very small amounts. Get near a black hole, time slows down a lot. Again, in the movie Interstellar, they actually used this when they were on a planet orbiting a black hole. 1 hour of their time was like years of Earth time because of this time dilation effect. Those same time dilation equations that we learned in special relativity that apply to moving really fast, they also apply to being in a high gravitational field. Okay, so if you're going to orbit real close to a black hole, you could have a time dilation effect with that 1 over v squared over c squared thing, whatever, creating a massive difference in t naught versus t. Okay, and so again, just some cool consequences of relativity that come out of the generalized theory of dealing with non-inertial frames. And again, I'm going to have to leave that for future courses to deal with once you have more advanced math under your belt. So that's it for relativity, finally. After this, the last remaining month of school, we'll go back and look at some other interesting selected topics, probably some optics that will be helpful for you in future physics classes. And that will be it for today.